All right, let's dive into the formal material that we'll see in Chapter 6 of our Perloff Microeconomics book. In our little intro to what we're going to be doing differently now, we talked a little bit about how when we're moving from utility functions into production functions, instead of talking about goods X and Y being the inputs to create utility, now we're talking about labor and capital. Capital we're going to spell with a K, even though that's not the right way to spell it in English, because C would confuse it with cost sometimes. And some product or some kind of service is going to be the output. And generally speaking, whenever we use more inputs, more labor, and more capital, we would normally expect that we get more output for it. To start off with, I wanted to look at an interesting production function that doesn't always have this characteristic, just to kind of let us see what some of the other possibilities might be. And then we're going to fall back into our normal production functions that we're going to use most of the time, which are going to be Cobb-Douglas. So instead of a utility function, now we're talking about a production function. And instead of having a utility function U equals, now we're going to have Q equals, and then we're going to have L and K for the number of units of labor and amount of capital we're using. And instead of marginal utility, we're going to talk about marginal product. So marginal product is how much additional units of output do I get for increasing the amount of an input by 1 unit. And instead of marginal rate of substitution, now we just add the word technical in there to let people know that we're talking about a production kind of situation. So let's look at this interesting production function here. Now this is the function over here, kind of crazy, has a lot of different exponents and a lot of different fractions in it. Don't worry about that for now. I just like this because it has this interesting kind of shape. In 3 dimensions, we see as we use more labor along this axis and more capital going back along the left side, our output usually goes up. But in this one, it actually has a maximum amount of output that you can reach. If we look at this circle up at the top, this little blue circle, that is the isoquant for 190 units of output. Now, the actual maximum is probably slightly higher than 190. Right at that red dot in the middle is probably maybe 191 units of output or something like that. But for some reason, beyond that point, if we keep adding more machines and more workers, our output actually starts to go down along the back side of this hill here. So this gives us some interesting things that we can look at down below when we look at the shape of these isoquants. Again, this isn't going to be the normal thing when we're looking at a Cobb-Douglas, but it certainly could be something that you run into in reality. So let's look at the isoquants down below here. So all these isoquants are is, what if we flew a helicopter up above this hill up here, and we were to look straight down, then this is what we would see, as long as we had these little contours colored in different colors for us. And here we see that little ring at the top for 190 units of output, and again, maybe right in the middle there, maybe we'll get a little bit more than 190 units of output. But as we increase our labor and capital beyond that, you see that our output will start to go down, 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 down. Now it's interesting to think, why might this happen in the real world? And what could be going on here is there's a third input. Maybe in addition to labor and capital, if we think about capital as say number of machines, maybe the other input that we're missing here is floor space in a factory. And if we try to cram more and more workers and more machines into the same space in the factory, perhaps it starts to get too crowded. And as we overcrowd our workers, output starts to go down past that point. So it looks like, now the first thing I want to point out in this diagram is when we're looking for optimum points in a situation like this, I want you to consider these 2 points. Suppose we wanted to produce, let's see, this is 190, 180, 170. Let's look at 2 different ways to produce 180 units of output. Let's call this, say, point A, and this point B. Now let me just make up what it looks to me like those numbers could be. At point A, let's assume that's 21 workers, and at point B, that's 22 workers. And let's assume at point A, let's call that, I know it's not exactly right, but let's call that 24 machines, and let's call B 22 machines, just for the sake of argument. Remember, when we're talking about the marginal rate of technical substitution, we can find that by looking at the ratio of the marginal product of labor divided by the marginal product of capital. And we can find those by taking the partial derivative of the production function with respect to labor and capital, respectively. If we're looking at a graph, marginal rate of technical substitution is just the slope between those 2 points, rise over run. And what that rise over run, that marginal rate of technical substitution, is going to tell us is the rate at which capital can be decreased for each 1 unit increase in labor, giving the same output. Or we can think about it as the rate at which capital must be increased for each 1 unit drop in labor to keep the same output. It just depends on whether we're thinking about moving between point A to B or B back to A. So we see when we move from point A to B, we're adding 1 worker, that's our run, and we're losing 2 machines. So that's our rise. Minus 2 over 1, so our slope is minus 2. That would be our marginal rate of technical substitution. And I usually like to think about this in terms of the absolute value. It tells us that between points A and B, that slope is 2 or minus 2, and if we add 1 worker, we could lose 2 machines. Or, if we lose 1 worker, we need to gain 2 machines. We need to add 2 machines to make up for that. Now, which of these 2 points is the best way to produce 180 units? The answer is we're not going to know until we know the price of labor and the price of capital. After we know that, we could figure out which of these 2 points would be the cheaper way to produce 180 units. But there are some points we can rule out as definitely not being the best way to produce 180 units. Let's compare these 2 points. Point C to point D. Now I want you to think carefully, pause the video if you need to. Why is point D absolutely not the best way to produce 180 units? If you said at point D we're using more labor and more capital than at point C, you're right. We know that point D must cost more than point C because you're using more resources and you're producing the same amount of output. D has to be worse than C. Similarly, C has to be worse than point E because at point E we're using less labor, but we're using the same amount of capital. So we can rule out points over here as definitely not being the best. Similarly, over here, we're using more labor and capital to produce 180 units than we are over here around A and B. So basically what we're doing here is we're ruling out any points on an isoquant where, in order to get there, we have to go through a positive sloped area. A positively sloped area means we're going to use more of both. We're going to use more capital and more labor. That's obviously a terrible idea. We can also rule out flat portions here where the slope is exactly 0 because we are using more labor and we're not getting more output. That wouldn't make any sense, so we can rule that out. And we can also rule out any points that are perfectly vertical, right? Because a vertical part would also mean we're using more capital, but we're not getting more output. So anytime you're going to increase your costs without getting more output, that's obviously a bad choice. These kinds of regions in an isoquant map like this, we call non-economic regions. Non-economic regions. We could just call them stupid regions if we wanted to, but we'll stick to the more technical term non-economic. It just means if you see any place where the marginal rate of technical substitution is positive, or if in order to get to that region, right over here, in this area, the slope is negative, but in order to get there, we had to go through areas where it is positive. And so, long story short, you know that if there's a way that is cheaper, where you're going to be using less of both outputs, that has to be better than one where you use more of both outputs. It's just common sense. One other kind of nifty thing I want to talk about here, and this is of interest in macro, but also in micro. Sometimes in macro and sometimes in microeconomics as well, we want to ask the question, how capital intensive is an industry? And when we talk about how capital intensive an industry is, we want to know what's the ratio of capital to labor. So capital to labor ratio. If we had one industry where we use 4 machines for every worker, that would be capital intensive. However, in an industry where we used 1 machine, 1 unit of capital, for every 4 workers, that would be a very low capital intensity kind of industry. A visual trick you can use in a graph like this is if you want to compare how capital intensive is one solution to another, you can visualize the capital to labor ratio by drawing a ray from the origin to a point. So for example, let's compare this point A to this point B and see which one is more capital intensive. If we just sit and think for a minute, we can obviously see that point A uses a lot more capital and less labor, and point B uses a lot more labor and a lot less capital. So we know that A is the more capital intensive point. But if you want to visualize the magnitude to which A is different from B, let's draw a ray from the origin to both of those points. And if you just kind of think, wow, that ray to point A is very steep, and the one to B is much, much flatter, the slope of the purple ray tells you the capital to labor ratio at point A, because the slope of the purple line is rise, which is from 0 to 15, over run, which is 0 to 4. The slope of that line is 15 over 4, which is the capital labor ratio. 15 units of capital, 4 units of labor. Similarly at B, it looks like the capital might be 6 and the labor could be 9, and that's the slope of this green line is 6/9 or 2/3 compared to 15/4. We can see with our eyes the difference in slope, and that very quickly tells our brains how much more capital intensive A is compared to B. And there are some problems where that comes in handy, just being able to visualize that quickly. We started off looking at this very interesting kind of production function that has this interesting feature where you have these positively sloped non-economic regions. Now, let's take a look at some more cases that we'll see. So most of the time, we're going to be sticking with our traditional Cobb-Douglas kind of production functions. And Cobb-Douglas production functions, because they're going to look like this, C times how many units of labor to some power times capital to some power, they're going to have this general kind of shape. They're never going to touch the X or the Y axes, because if you touch an axis, that means that one of those two values is 0. In this kind of production function, if it's Cobb-Douglas, we're assuming that if you have no workers, you can't produce anything. We're also assuming if you have no units of capital, you can't produce anything, even if you had 1 million workers. Cobb-Douglas production functions also, when we look at their isoquants, always have a negative slope to them. And so we're never going to end up with those cases where we have non-economic regions. Another common case that we like to talk about with production functions is called a Leontief. Vasily Leontief was a mathematician who did a lot of work in economics, and back when he was studying economic problems, he was mostly looking at things, say, like shipping using trains. And when Leontief looked at production functions, he assumed that people and machines were perfect complements. Perfect complements means that people and machines have to be used in fixed ratios. So let's suppose we were talking about a train. Capital here on the y-axis, labor as always on the x-axis. Leontief might look at a train and say, okay, in order to make a train run, you need at least 3 people. Perhaps you need a driver, you need a fireman to shovel coal into the train, because this was a long time ago when Leontief did his work, and perhaps also you need somebody we'll call a brakeman, the person that stops the train. And so if you need 3 people for every train engine, then you could get a certain amount of output if you had 1 unit of capital and 3 people. But with a Leontief production function, you would assume that if you just added more train engines, you're not getting more output. So they would be on the same isoquant. Similarly, if you just added more workers without adding more train engines, you would have the same amount of output. So 1 train engine and 3 workers, maybe that would be the isoquant for 100 units. Maybe 1 train engine and 3 workers could haul 100 tons of coal, for example. But you're not going to get any more output unless you get 1 more engine and 3 more workers to run it. So the next isoquant would look something like this. And maybe that would be for 200, or it could be 150, just depends. So this would be a Leontief production function. When you look at these production functions mathematically, usually they're going to look something like this, that the amount of output is equal to the minimum. Since we need 3 workers for every train car, let's see if this would work. The minimum of the number of train engines and 3 times the number of workers. Now, and then we could also multiply that by some constant, maybe 100. Let's see if this works out. So for this purple one, right at this point, we have 1 train engine and 3 workers. 1 and 3. No, looks like I've got it wrong here, because we have 3 workers and 1 train car. So the minimum there would be 1. That would kind of work, but what if I added 2 train cars? Now the minimum would be 2, and that seems to suggest that we would get more output, but that's not what we said here. Let's try this a different way. Maybe we should have the minimum of the amount of capital and 1/3 times the number of workers. Let's try that out. So if we had 1 machine, and then we add 1/3 times 3, okay, well that would also be 1 times 100. Well, that would give us 100 units of output. What would happen if we added another train car without adding any more workers? We still had 3 workers. That would put us here. 2 trains, still 3 workers. We're on the same isoquant, so yeah, I think we got it right that time. So the long story short, if you see a production function that has a minimum in it, it's probably a Leontief production function. Another example is, what if we had perfect substitutes? Perfect substitutes means maybe we have robots and we have humans. We can use either one. They can do exactly the same things as each other, and we can perfectly substitute between them. Let's suppose in this case that robots are twice as good as people, twice as fast. So 1 robot equals 2 people in terms of effectiveness. So let's think about what these production functions would look like if we look at their isoquants. So if we had 1 robot, that would give us the same amount of output as 2 people. There would be an isoquant. 2 robots is the same as 4 people, or we could have another point in the middle here, 1 robot and 2 people, right? And so if we have perfect substitutes, we're assuming those are straight lines, 3 robots, 6 people, or 2 and 2, or 1 and 4. Perfect substitutes means that there's no curvature to the isoquants, that you can smoothly, perfectly substitute every time. Lose 1 robot, substitute 2 people. Lose 1 robot, substitute 2 people there. So the marginal rate of technical substitution, always constant. With the Cobb-Douglas, of course, it's going to be steeper over here, high marginal rate of technical substitution, and lower over here. Leontief, the slope is either 0 or infinity. So no substitutability at all if you're talking about a Leontief or perfect complements kind of production function. All right, I'll end this video here, and in the next video we will talk about some ideas associated with maximizing output, minimizing cost. We'll talk about marginal product of labor, average product of labor, and some other interesting topics. So I hope you'll join me for that. I'll talk to you later. Good luck, everybody.